This is number 4. This is a non-calculator problem for area volume FRQ. We have this shaded region here. Shaded region is in the first quadrant, bounded by the graph of y equals 2 root x. That's the radical function with the curve here. The horizontal line y equals 6, and the y-axis that closes off our boundary for our shaded region. For part A, it says find the area of R. So to find the area of R, maybe it's just easiest to just do it in terms of top minus bottom, since we have our equations already represented as functions. So we do top minus bottom here. But we do need to find this without a calculator. We have to be able to find our numeric value working our way through our definite integral. So here's my rectangle that represents the distance between my top and my bottom function. So the top is sitting at the 6. The bottom of my rectangle is sitting at the 2 root x. So 6 minus 2 root x, that represents that height of that rectangle. The dx gives it that second dimension, and then we can able to move from height to area. We're accumulating these rectangles from one end to the next. We start at 0 and we go all the way to x equals 9. Okay. So 6 minus 2 root x, we can go through power rule, but first I'm going to set up 2 root x to be 2x to the 1/2. So these are two separate terms. We can apply power rule separately. 6 becomes 6x. Right? When we do power rule for integrals, we increase our degree by 1. So 6 was x to the 0 power, but now it becomes 6x to the first power. And then for 2x to the 1/2, we add 1 to the exponent, and we divide it by that same exponent. So 1/2 plus 1, the same thing as 1/2 plus 2 over 2, which is 3/2. So 3/2 over 3/2, the coefficient stays. And we have our antiderivative. Now we can plug in our upper and lower bounds. Again, these upper and lower bounds do not touch this integrand. We have to push this through our antiderivative rule first, and then the bounds gets used. So now we have our antiderivative. We plug in our upper bound. 9 plugs in for x. Then 9 plugs in for x here. We get 54 minus 2 times 2/3. This becomes 4/3. 9 to the 3/2, the same thing as square root of 9. That 2 means square root. Square root of 9 is 3. 3 cubed is 27. So we get 54 minus the 3, and 27 becomes 9. So 54 minus 36, we get 18. For part B, write but do not evaluate an integral expression that gives the volume of the solid generated when R is rotated about the line y equals 7. So here is my shaded region. My axis of revolution is going to be y equals 7, which you can tell there's a noticeable gap between the shaded region and the axis of revolution, which means that we have to subtract out that hole, which means that we have to go through Washer method. So to do Washer method, we're going to draw our two rectangles. Two radius. One radius that starts on the dotted line and extends to the further boundary of our shaded region. And then little r extends from the dotted line axis to the closer of the two regions. So you can tell that big R is longer than little r. So we do top minus bottom. The top of big R is sitting at the 7. The bottom of big R is sitting at the curve, which is 2 root 7. So my big R is 7 minus 2 root 7. My little r is 7 minus 6. That's the length of the little radius. Okay. Our bounds is from 0 to 9. Okay, still in terms of x, so we still go from 0 to 9. And we do pi, big radius squared, minus little radius squared, dx. We just have to set it up. We don't have to find the actual volume. It says write but do not evaluate. Okay, for part C, we have region R is base of a solid, so we're doing cross section here, but we have to then decide how to draw our base length. Are we going to draw it vertically, or are we going to be drawing it horizontally? So the problem says perpendicular to the y-axis, so let's think about what direction that is. Y-axis is vertical. So perpendicular to a vertical line must be horizontal. So we want to draw a horizontal base that will represent our base length. So here's my base length that I drew horizontally. But if we do horizontal base length, that means we got to do right minus left. If we do right minus left, that means the equations that we have given to us is not in the correct form. We have to get it into as the form of x equals. So right now this is in the form that is good for top minus bottom, but it's not in the form that we need for right minus left. So for the 2 root x equals y, I need to be able to solve for x. So divide by 2, square both sides, I get x equals y over 2 quantity squared, which is really y squared over 4. The left is this y-axis, which has an equation of x equals 0. So we have y squared over 4 minus 0. That is the length of our base. If we go back to our problem, the problem says that we want to create a rectangle that is 3 times the length of the base. So we have to identify what is the area of that rectangle. So the area of rectangle is base times height. We have the base already, we just have to represent the height. The height is given to us as 3 times the base length. 3 times the base length. So my base length is y squared over 4. So this is my representation for my height. My base is y squared over 4 times the height, which is 3 times y squared over 4. I put all that together, I get 3 y squared over 4 quantity squared. This is an area representation, and if I just put integral from 0 to 6 and dy on both sides, then I can move from 2-dimensional to 3-dimensional calculation. And the reason why it's 0 to 6 is because everything's in terms of y, so our bounds have to be in terms of y. We find the lowest y value, we find the highest y value, and those are the bounds we use. For part D, write but do not evaluate an integral expression that gives the volume of the solid generated when region R is rotated about the line, a vertical line, x equals -1. So it's no longer a horizontal line that we're rotating around the vertical line. So that vertical line is at x equals -1. So here's my radius. There's obviously a gap between the axis of revolution and the shaded region, so we know it's going to have to be washer method again. But now the radius that we're drawing is no longer vertical. It has to be perpendicular to our axis, so we're going to extend horizontally from the axis to the further of the shaded region, and then little r is going to extend from the axis to the closer of the two regions, and then we're going to do right minus left. Now the equations that we're going to be using, we can reuse from part C when we were doing right minus left for cross section. So big R is going to be y squared over 4 minus a -1. Okay, so that's here. The two negatives become positive, so y squared over 4 plus 1. And then little r is going to be 0 minus -1, so we have that here. The two negatives become positive, which is positive 1. Our bounds is still going to be in terms of y, so lowest to highest y value from 0 to 6. Washer method, pi, big radius squared minus little radius squared. And we just have to set it up, no need to enter in our calculator.